All right. Yeah, welcome everybody to the WISE lecture series, a public lecture series on topics of sustainable energy. And we're very excited today to have Carlo Adamo from the Institute Universitaire de France. I hope my pronunciation is not too far off there. Here with us today. He's the chair of theoretical chemistry at this institute in Paris. And Carlo Adamo completed his master's and PhD at the University of Naples in Italy, and as I said, is currently the chair of theoretical chemistry at the Institute Universitaire de France in Paris. And his main research interest is on DFT calculations, density functional theory calculations, and the applications in energy context. So really bringing the theory to the experimental and trying to gain knowledge.
Some insight on the.
And we're very excited to hear today some of your experience. He's also author of a large number of really relevant publications. Is editor as well of the Physical Chemistry, Chemical Physics, PCCP, an RC journal, which is one of the standard journals in his field. And he's also co-author of the Gaussian code, if I'm correctly informed, which is the standard every theoretical chemist uses nowadays. So we're very excited for your lecture and looking forward to it. And the floor is all yours.
Thank you for the presentation. First of all, I would like to thank Professor John Wen for this kind invitation, and also the WISE Institute to give me the opportunity to talk about our work concerning dye-sensitized solar cells. Just a transparency about our institute. Actually, it's Chimie Paris-Tech. It's a chemical engineering college founded by Charles, the guy of the Friedrich reaction, more than 1 century ago. It is located in the heart of Latin Quarter. It's really in Paris, downtown. Essentially, this is a chemical engineering college, and the idea of Charles Friedel was that a chemist who intend to industry will have a scientific education as strong as those who want to devote himself to scientific careers. Actually, it is a relatively small institute. It is 8 laboratories, about 100 research, plus 100 technicians, 90 students. And my group, the group of modeling of complex systems, was created in 12 years ago upon my arrival in Paris. Basically, I will talk about this relatively new device called dye-sensitized solar cells. I give you some information about the basic working principles. Then, I'm sorry, but there are a few transparencies about theory, just to define our computational protocols, and how these protocols can be applied to what I call the classical DSSC. This means the cells composed by ruthenium dye over titanium oxide, the so-called Grazer solar cells, is still the standard in the field. And two relative new systems is eosine over zinc oxide. Then I will talk about new dyes and how these dyes interact with zinc oxide, and the effect of additives and solvent coabsorption and conclusion. They say that through my talk, they say how theory can bring information to the experimentalists and how this information can be used to experiment to improve the efficiency of solar cells, either using, for instance, a new system or just to add some new ingredients to the solar cells. The key components in dye-sensitized solar cells, of course, is the dye, who is in interaction with a semiconductor. This interaction is essentially like there are nanomaterials, it's nano interactions. So you have the dye, which is in contact with the semiconductor, and this dye is excited from its ground electronic state to the first excited states upon the arrival of a photon. At this excited state, high in energy than the conduction band of semiconductor, so that you have injection of one electron from the dye to the semiconductor. And this, of course, generates electricity. At the same time, the dye goes back to the ground state, of course, as a cation, and this cation is regenerated by a redox pair, like I3 minus, I minus. Here, this is present in the solution, so that the circuit is closed. As a theoretical chemistry, I am very happy to work on real devices, even if these are, for the moment, in more gadget, like this self-energy generating gases, or like the solar windows. This is the idea is to use this the peculiar property of this device to transform a passive element like the glass of a window in active element producing energies. Sony produced a lamp, we call it an Akari, where all the side of the lamp are the panel which generate electricity for the light inside. And this backpack is the first commercial application. You can use this small panel to recharge your iPhone or iPod or whatever you want. Of course, this system is very complex for a theoretician, so the first step is to decompose the problem in elementary steps, what we can study. For instance, we can study, or we have studied the properties of the dye, the interaction of the dye with the redox pair, with the solvent, or with the surface. We have studied the mechanism of electron transfer from the dye to the semiconductor, and of course the property of the semiconductor, the surface of the bulk properties. In this sense, this system is characterized by a large variety of phases, properties, interactions. We have solid states, we have molecule, we have solvent, we have system in ground electronic state or in excited electronic states. And we want to study this at quantum level. Since we are interested in electron transfer reaction, basically force-induced electron transfer reaction, our elementary brick should be electron. So we need tools coming from quantum chemistry. And in particular, we are using a tool which is called density functional theory. In short, in this approach, which is formally exact, the energy is a function of the electron density, and is composed by 4 parts. One is the kinetic energy of the electron. The second part is the electron-nuclei interaction, the classical electron-electron interaction, and then you have 4th term, which is called the exchange correlation energies, so that when this term is summed to the other 3, this is the exact energy of our system. The exact energy of the system, this means the energy coming from the exact resolution of the Schrödinger equation associated with our systems. Unfortunately, we don't know how these terms depend on the electron density of the system. This means that we need to approximate, and there are a lot of models to approximate this exchange correlation term. We developed more than 10 years ago our own models, which is called the PB0, and basically, let's say this is what we call the functionals. And what we want to do is use this PB0 approach, the same DFT approach, for molecules, surface, and bulk properties, either in gas phase or in solution, and in ground and excited electronic states. This means it's very challenging aspect. It's just one tool for everything in the solar cells. Of course, we need a validation step. We need to validate our approach. For instance, we have carried a lot of benchmarks on the absorption property of organic and inorganic dye. Here you have, for instance, you have the mean average deviations computed with different DFT approaches for about 200 valence excitations or 210 valence plus radio excitation, and you say that our approach, the PB0, is the one providing, one of the method providing the lowest deviation. This is around 0.1 EV. It could be less for some specific family of dyes. We can also use zinc oxide. We can validate our method for the zinc oxide. In such a case, we have a good agreement between the computed gap in bulk zinc oxide and the experimental value, especially for this. Well, the gap is we are few tenth of electron volt higher than the experimental value. And the same also for surface. In such a case, this is the relaxation of a surface with respect to the bulk properties. They say that we can reproduce the experimental value concerning the structure of the surface. So once our method has been validated for the general components, dye and the semiconductor, we can see a little bit more in details our standard systems. This means the ruthenium absorbed on titanium oxide or the dye eosine absorbed on zinc oxide. Ruthenium dye, this is the reference in the field. If you have ruthenium or eventually osmium, then you have the two BP reading and two ligands here to tune the photophysics of the systems, and of course the carboxylate to anchor the dye on the surface. This is instead this is eosine. This is a commercial, very cheap dye, and once again you have carboxylate, which is necessary to anchor in a covalent way the dye over the surface. These cells is characterized by 11% of efficiencies. This means 11% of the light is converted in energy, and this one, eosine of zinc oxide, is characterized only by 2%. And the idea is to understand this difference, why this is more efficient than the other one. Of course, the further starting point is to reproduce the optical properties of the dye, and here is 4 and 3 dyes with either ruthenium or osmium metal, and the ligand could be CN or NCS. And you say that here this is the dye in the gas phase. This is the computer value for the dye in gas phase. These are the computer value of the solution value for the dye in solution, and this is the experimental value. They say that it's a quantitative agreement for this dye, and was transitional, basically MLCT transition, metal to ligand, an excitation 1 electron from the metal to the ligand type excitations. And what is most important is the effect of the solvent on the spectra of this dye. This is in blue. This is the UV visible spectra of this dye computed in the gas phase, and this is in orange. This is the computed UV visible spectra in solutions. I say that there is a significant shift, and also the shape of the absorption spectrum change in a significant way. The orange profile is, as we will see, in excellent agreement with the experiment. So then we can absorb this molecule over the surface, and we can compute this assembly. This means the die over an titanium oxide surface or eosine over zinc oxide surface using DFT and the periodic boundary conditions. This means that our system is virtually infinite in 2 dimensions and is finite in the 3rd dimensions, so that we can, for instance, reproduce the coverage, the experimental cover of the die, the experimental density of the die over the surface. The results of this simulation is are the density of states. This means the electronic structure of systems. And you say that, for instance, in the N3TO2 systems, the HOMO, the highest occupied molecular orbital, is localized on the die, whereas the LUMO, the lowest unoccupied molecular orbital, is localized on the surface. This means that, roughly, in the first approximation, the excitations is from this orbital to this occupied orbital to this virtual one, which is so we have injection of the electron on the surface. If we look at the other system, eosine over zinc oxide, you say that LOMO is localized on the die, but also the LUMO is localized on the die. This means that the first photon absorbed is just excited 1 electron from the die to the die, no injections. The second orbital, the second virtual or empty orbital, is delocalized between the die and the surface. This means that is the second photon, which is lead to an injection of 1 electron. So we already have some insights about the difference in efficiency of these 2 cells. Another way to say the same thing about injection is to compute, to reduce the systems. It is that we had a spare electron, and you say where this spare electron is localized. This localization can be visualized computing the spin density map. This means the electron density of spin alpha minus the electron density of spin beta. In this case, in the case of N3TO2, the density is completely localized on the surface. This is 100% on TO2. The spare electron is on the surface. If we add an extra electron to the eosine zinc oxide system, just 30% of this electron is localized on zinc oxide. And if we add 2 electrons, we reduce 2 times our system, 50% of 2 electrons, this means 1 electron, will be localized on zinc oxide. Still, we can, from these periodic boundary conditions, DFT PBC calculation, we can compute also the injection time. You say that in picture derived from molecular orbital, this is the semiconductor, the valence band, the band gap, and the conduction band. Here we have the orbital of the die. The LUMO interacts with the orbital of the conduction band, and upon this interaction is spread by the interaction with these orbitals. And the injection time, using a simple model like the new Anderson models, is inversely proportional over the width of this spreading, so that with this model for the N3TO2 system we can compute an injection time of 22 femtoseconds, which is comparable to 20 or 50 femtosecond experience. And also for the system composed by bipyridine decarboxylate, just the ligand of N3, the experiment is less than 3 femtoseconds, we compute 2 femtoseconds. Of course, for the system eosine zinc oxide, there is no injection because the LUMO is at this level. But for reduced systems, we can compute 8 femtoseconds. And this results induce us to propose a way to improve solar cells. They say the standard solar cells, as I said before at the beginning of my talk, this is the dye in ground state is absorbing one photon. The excited state is higher in energy than the conduction band, so you have injection. This is the standard way of working for N3TO2. If we go to the other systems, we can imagine that the dye in ground state is excited. The excited state is lower in energy than the conduction band, so no injection, but can be then reduced by an external agent so that this reduced species can be excited once again, and then we have injection. And this is what we have proposed in our work to improve the efficiency in these systems. From the DFT calculation, we can then extract a large cluster representing the surface plus the dye, and then we can compute the in situ absorption spectra of the molecule. This means with the spectral molecule of the surface using an QM prime approach. This means that our system, we use two different methods, one for the surface and another one for the dye. Originally, the particularly our approach that we use what is called electronic embedding. This means that the two systems, surface and the dye, are coupled through an electrostatic term. And here, on the right, there is the experimental spectra, and on the right, on the left is the computer spectra. The blue spectra is the spectra of the eosine in solution. You say that the shape is the same. There is just a shift of about 50 nanometers. And in orange, there is the spectra of the eosine over the surface. And once again, the shape is very similar to the experiment. The two here, the two are normalized. This is not the case for the theory. And the same can be done for the system N3 dye over the surface. You say the system is quite large. It's about 1,000 atoms. This means that the computations are relatively heavy. And here this is the experimental, part of the experimental spectra. You say that here this is the computer spectra. Yes, in blue is the molecule absorbed on the surface. In orange is the molecule in solution, and in green there is the molecule absorbed on the surface and then plugged in the solution. I say that the effect of the surfaces is negligible. What is important is the effect of the solvent around the dye. So, what we are learning from these standard systems? Basically, we have developed computational protocols in which the first step is the pre-screening of the dye, based on the calculation carried out on the isolated dye, or the dye in solutions. And we can select a dye using three criteria. One is the energy criteria. This means that the lumen of the dye should be higher in energy than the conduction band of the semiconductor. Then a second criteria is the dipole criteria. This means that the dipole of the molecule should increase upon excitations, and this electronic excitation should correspond to a charge transfer toward the surface. If we apply this first step, then this leads to a selection of a number of dye. We can select some dye, and from the selected dye, we can start. For the selected dye, we can study the interaction with the surface, for instance, with the zinc oxide surface, using our periodic approach for the solid states. And then eventually, as we'll see, we can add other effects like effect of solvent or additive, etc. The fact that we use the same DFT approach for the molecules, this is step 1, or for the periodic system for the surface, is somehow grant us for the transferability of the results. This means we always use the same method, so the error is somehow constant, or we hope to be constant for the different properties. So, with this model, we have started a study concerning new dye. These new dye are composed by an electron donor, an acceptor, and between the two there is a spacer, and of course an anchor group. The idea is that in excited state, we have a charge transfer excited state were characterized by a charge separation. And we started with experimentalist colleague to design, just on the paper with pencil, different molecules, and then from this original 30 molecules we select 6 molecules. We are characterized where the acceptor is in pyridinium systems. The donor is an H2, it's very simple electron donor, and then we have 2 family. One is this 3 is branched molecule, or this 3 are diffused one. You say that we can have 1 or 2 pyridinium-like system. All these systems are characterized by a strong absorption in the visible range. These are the computed electronic transition. This is the first aspect, the first part of the study. And this band corresponds to the charge transfer. And here we report the difference in electron density from the ground to excited state. Green is increased, red is decreasing during excitations. Then we have selected one, is not this one, which has been sensitized by our colleague, and we can compute, of course, also other properties. For instance, the color of these molecules. This is the theoretical predicted color of this molecule. Let's say that this one we have in the red region, which is very interesting because in this region there is the peak of the solar intensity. So this has the absorption in the right wavelength region. And this molecule has been sensitized. Is the red is the experimental absorption spectra, and in black you have the computer vertical transition. I say this is an excellent agreement between theory and experience. And so these molecules fulfills the 3 criteria in the first part of our protocol. This means that the LUMO of this dye is higher, slightly higher than the conduction band of zinc oxide. There is a large increase in dipole in going from ground excited state, and the transition corresponds to a charge transfer band toward from the donor toward the acceptor. This means toward the surface. Then, at that point, the second step in our protocol is to study the interaction of the dye on the surface. If we just absorb this molecule, since this molecule is charged, we have this kind of parallel arrangement of the dye with respect to the surface. This is not physical. So we need to add some solvent, for instance, water molecule, to have more realistic structure of our system. And then, of course, we can look at electronic structure. This is the density of state for the system composed of dye, zinc oxide, and water molecules. if we look more in details, we say that the lumen of the dye is lower in energy than the conduction band. Since the dye interacts with the surface and the structure dye is deformed, of course, the lumen decreases in energy, so that the energy criteria that we have defined before is not longer fulfilled. At this point, we have two, so an injection, of course, is not favored. We have two possibilities. One is to change the lumen energies upon functionalization of the dye. We can chemically functionalize the dye to reduce, to move the lumen energy, to increase the lumen energy. A other possibility is to work on the conduction band of the semiconductor. This means we can add some additive to our systems. We are choosing this second way. For instance, we can add lithium atom. What's happening if we add lithium atom to our system? Say that the gap between lumen and the conduction band is strongly reduced, and now lumen is very close to energy, so that injection should be possible. This is always theory. If we add an pyridine derivatives, like for instance methylpyridine derivatives, the gap between lumen and the conduction band increase, and we have even a second orbital of the dye which is lower in energy. The same picture, we can reduce, we can add a spiral electron to our system and say that in the reference system, dye and zinc oxide, only 20% of the spiral electron is localized on the surface. If we add lithium, we found 40% of the dye of the electron localized on the surface, and instead, if we add pyridine derivatives, we have just 90% of the electron which is localized on the surface. With this information, we went back to the experimentalist, and these are the photocurrent plots, the experimental photocurrent plots of device. This means that you have the incident photon to electron conversion efficiencies as a function of the wavelength, incident wavelength. In red, there is the plot for the system without additive. If we add terbutylpyridine, the efficiencies decrease. If we add lithium, the efficiencies increase. This means that there is a qualitative agreement between the theory and the experiment. But, of course, we can do better, starting from our calculation for the molecular excited state. We can simulate the IPCE plots that I showed you, starting from a convolution with the Gaussian of each transition. Then this transitions are weighted for the spin density I show you. I weighted by the spin density that I showed you before. And a small integration over the solar spectrum, and then you arrive to this kind of plot, which is exactly the same you find experimental level. Here you have the photocurrent plots from experiment, and this is the photocurrent plot coming from our quantum chemical calculation. I say that agreement between theory and experiment is not so bad, it's good. And so this means that starting from the microscopic properties, the electronic structure properties of the system, we can predict a macroscopic property of the solar cells. So this is the conclusion. This means that now we have an ab initio approach, an approach based on the quantum chemistry method, for not only the understanding of the elementary step phenomena in dye-sensitized solar cells, but also this method can be used to predict, to design new systems for solar cells. It's based on the study of isolated molecules, in particular on the property on interaction of the light in the molecules, like the absorption or the emission, or the strain of these interactions, on the excited state properties, like the change of dipole moment or the density, and then on approach concerning the interaction of the dye with the semiconductor, which give information on the structure and electronic properties, which also allows for the calculation of injection time and the prediction effect of co-absorbed molecules. Of course, I have to thank some collaborators for this work, and in particular Ilaria, Frederick, and Tanguy. They are people in my group, of course. Then Thierry for the preparation of the solar cells, and Philippe for the synthesis of the new dye. Denis and Don are involved in the aspect concerning the benchmark of the method for excited states, while Mike, Rant, and Krishnan are involved in the study of the absorption effect, of the molecular absorption effect on the electronic spectra. EOF, CNRS, and INR are also thanks for the funding, and of course you for your patience for to be here to my talk. Yes.
Yeah, thank you very much for this very interesting lecture. And are there any questions? We have quite a bit of time for discussion.
Yeah, actually I would like to know, because you didn't really explain the formulas you really use to modelize the different parts of the solar cell, and I would like to
For modelize the different
like
part.
the equation like you use to modelize like this part and this part, this interaction, this kind of.
You are talking about our method that we use for.
Yeah, because at the end, like you calculate the current you can have. So I was wondering how you do that.
Okay, this. Okay, basically, this is the let's say the vertical transition that we just have using from our DFT calculations. Okay, this is a quantum chemical calculation to give you the difference of ground and excited states. Okay. If you want to explain this, needs a class in quantum chemistry, so we need something like 20 hours. Okay. Then I can convolute this transition with a Gaussian function, which is a standard technique. Okay. This is in reality the transition is not just if I can. Okay, this is your ground state, this is your excited state. In a perfect world, it could be just one line, which is what we compute. In reality, you have the solvent effect, thermal effect, the Heisenberg principle. So this is not just a stick, but it corresponds to something like this, because it's a thermal motion or solvent effect, order effect, or quantum effect, whatever. So we just fit this with one Gaussian functions. The surface of this Gaussian, this part, is proportional to the intensity. Okay? Then we weight this function using using these spin densities. Okay? And this gives this plot, this curve. Then this curve is related to J, to the what is called the short circuit current density. This simple formula. This is the solar spectrum. This is the wavelength which you compute your J value. Okay, this is just the solar spectrum, and then you arrive at this plot. Of course, you need all the transition, all the part concerning the excitation, but I said before is you need a class in quantum chemistry. I say that the method is very accurate for the calculation of spectra. The error is also on the valence excitations is between 0.1 and 0.2 eV.
Yeah, how did you measure the IPCE from measurement for experiment start?
How are you?
For the first thing, how did you measure it? It's like a
How I match? No.
how you measure? How did you measure the value of the IPCE?
The match between experimental theory?
Yeah. So I understand how do you calculate.
Yes,
right?
okay.
But for the measurement, experiment study, right?
Yes.
Yeah, did you just?
I can measure. Honestly, I don't know because this has been carried. This is the TRD who carried out the experiment. So I don't know exactly how this is done. I suppose that he has a kind of solar simulator. He has a kind of solar simulator. It's a kind of single photon experiment.
Because efficiency is very high, right?
Here, its efficiency is very low.
Oh yeah.
This is very low. Basically, we are around 2% with this, but the die is new and has not been optimized. The die. What is interesting behind the system itself is the computational protocol. So we tested this computational protocol on new systems. So we use this computational protocol to design this new system. Then the system is not as good as we expected, but we can reproduce the macroscopic properties of the system. And the die could be improved because, for instance, the donor is this is not the best donor that.
So for the modeling, you mentioned that the model works for both the bulk material and also surface.
Yeah.
So that's for the zinc oxide only, right? Or
we also for titanium oxide is the same. We are studying nickel oxide. So you have the injection of, in such a case, you inject not the electron but the hole.
okay.
And we're just for the moment studying the electronic structure on nickel oxide.
Yeah. You also mentioned about the continuum, like a solvent model.
Yeah.
So how do we integrate the DFT into that?
The solvent model we used is a continuum model. This is true either for the molecule or for the surface. Basically, we can imagine that we have a solvent which is not structured. Then we create a cavity, a molecular cavity inside the solvent, and this is the shape of the cavity, for instance, for an N3 dye. And then we put the dye. So to create the cavity, of course, needs some energy. This is a cavitation energy. Then we put the dye inside the cavity, and we switch on the electrostatic interactions. This means that the electronic distribution of the dye polarizes the solvent, and this polarization is represented by the appearance, the creation of charges on the surface, particularly in the middle of these triangles, and this charge polarizes back the solute, and then you have a self-consistent approach. This solvent molecule works well if you don't have specific interaction between the solute and the solvent. For instance, you don't have hydrogen bonding between the solute and molecules of the solute and the molecules of the solvent, and which is always often the case for the system, which is basically acetonitrile, whatever.
Can you?
Sorry.
Can you already predict or draw some conclusions on the design of the dye itself, on recommendations?
Now, what is say à la mode in the field is to have dye composed, this kind of dye, and with a donor acceptor. In such a way, you improve the injection of the electron on the surface. Of course, the anchor should not have an effect. Obviously, this is often orthogonal to the photosensitized part. What is important from a theoretical point of view is that it's not to look at the electronic structure of the dye, isolated dye, is not enough, because say the dye, if it is not rigid, can be deformed by interaction on the surface, and so its electronic structure is modified. So a rigid dye should be better, like is the case on N3. Ruthenium N3 dye, which is for the moment is still one of the best dye in the field. But of course, organic dye are cheaper than transition metal complexes. So from one modeling point of view, this is a discussion with the colleague, with the competitors, is to have correct information. You must consider dye and surface at the same time with interaction.
There was another question.
For your for the surface of the semiconductor you were choosing,
Yeah.
but for zinc oxide you chose some non-polar surface.
Yeah.
What's the effect of different surfaces? Would they, because if you choose a different surface of zinc oxide,
but polar surface, to model polar surface is still a big challenge for us, because to model polar surface you need to localize the charges, okay? And this is one of the main drawbacks in with DFT, which not like localization, it prefers delocalizations. So if you try to optimize to model the polar surface, you have a strong surface reconstruction, you end with a non-polar surface.
what about titanium oxide?
Sorry?
What about titanium dioxide?
The surface, the titanium size, it was unattached, it was an experimental surface, actually. For zinc oxide surface, exactly since this system are basically nanostructure, they don't know exactly what is the surface on which the dye is absorbed. So we studied what is the most stable surface at a theoretical level. Okay?
Because as you said, you're using nanoparticles. There is no well-defined surface.
Yeah.
You don't know which.
Yeah. No,
It's interesting that it's matching so well with the experiment.
Yeah.
And, well, it also makes sense that the
Exactly. What is the most at the computational level? It's of course our surface are perfect surface. Just modeling with this means we are no defect for the moment. Whatever.
And also the band gap value that you're getting for zinc oxide or
Yeah.
titanium oxide. How thick is
the surface? Honestly, I don't remember, but in the first part of the study, we check always the convergence of the band gap at the electronic structure with the thickness of the surface. And this is, of course, fundamental because we want to correct reproduction of electronic properties. This is also one of the reasons we use the same functionals, and it's a hybrid function for the molecules and the surface. So we try to minimize the error coming from the computational tool. But this is, we check if this is
so how big the cluster gets really big if you want to
the clusters, this is not a cluster. This is a periodic boundary condition calculation. This means that you have unitary cells containing, this is about 300 atoms, but this is a periodic boundary condition. This means that this unitary cells is translated in 2 dimensions, so you have virtually infinite systems. If you use clusters, you have another problem because clusters are better representation of the surface. Due to quantum confinement effect, the gap in the cluster does not correspond to the gap of the surface, so that the conduction band is higher, exactly, is higher, and also in this case, the lumo of the dye is in the band gap, which is does not correspond to reality, because if you have these situations where this is a conduction band and this is the lumo, which is lower but close, this means a due of 7 injections. This means that you have a thermal effect, because temperature move this, and so you inject, which is not observed experimentally. This is also another scientific discussion we had with some colleague. We carry out the first works on this system. They use a cluster. Then they need to invoke a thermal effect to justify the injection, but this thermal effect is not observed experimentally. And if you move from cluster to PBC, you don't need, basically you don't need to invoke this.
Sorry,
yeah.
You have a periodic boundary condition in here, which it's a superlab. Instead, if you want to repeat this is a unit cell, right?
Yeah, this is a unit cell. This is unit cells. It's a part of unit cells. There are more layers.
Oh, I see.
Yeah, there's more layer. Yeah, I don't remember exactly the number.
If you repeat it, the dye will be down again, right?
No, you are repeating just in
the 2D.
In 2D, and then it's infinite.
Yeah, but if it's 2D, still the thickness.
It's always the same.
That can show you quantum
No, you don't have. You don't have. In such a case, you don't have quantum confinement. They say you have two. This is finite in this direction. Then is in the other two is infinite. Okay. And the coverage of the dyes corresponds to the experimental coverage in such a way. So this means that the size of unit cells is chosen.
It's big enough.
It's big enough, exactly.
Thanks.
Computational, did you use just Gaussian?
No. For the molecules, we use Gaussian, but for the PBC calculation, we use the code which is called Crystal, which is a code working localized in Gaussian type orbitals. In such a way, we have exactly the same functions, a similar basis set for the molecular and the PBC calculations. I am a chemist. I don't like when plane waves. So the exchange correlation function is the same with the crystal and with the Gaussian basis set is similar. If you compute this molecule, the crystal, you have exactly the same result with Gaussian. So for me, it's easier. And if I suppose you are a theoretician, you can compute a Mulliken population in a similar way.
Okay. If there are no more questions, then please join me in thanking our speaker again.
Thank you. Thank you very much.